Welcome back, Focus Learners, to another explainer. So today we're looking at something you've absolutely seen hanging on the wall of, well, basically every science classroom you've ever walked into. But we are not going to just look at it as some static, boring poster. We're going to decode it. We're talking about the periodic table. And by the end of this explainer, you're going to see exactly why it's the ultimate intuitive decoder ring for literally all of chemistry.
It's a massive question, isn't it? Seriously, how do you organize the universe? When you think about it, everything around us, from the device you're listening on right now, to the air you're breathing, to the coffee in your cup, it's all made of fundamental building blocks. But if you just have a giant random pile of fundamental building blocks, you just have chaos. So how do we actually make sense of it all? To truly appreciate the solution, we kind of have to understand the sheer scale of the data problem early chemists were facing. Back in the year 1800, humanity only knew of about 31 elements. That's a pretty manageable list, right? But today, we have 118 known elements. Trying to memorize the individual behaviors, reactions, and weird little properties of 118 distinct chemical building blocks without some sort of system? Yeah, practically impossible. Okay, let's dive right in. Our roadmap for today is 1. The ultimate cheat sheet. 2. Evolution of the table. 3. Anatomy of the elements. 4. Decoding periodic trends. And 5. The power of prediction.
Section 1. The ultimate cheat sheet. Why even bother with classification?
Section 2. Evolution of the table. From chaos to order. Humanity made some really fascinating attempts to solve this massive data problem and efficiently group similar elements together over the years. We started way back in 1829 with Dober-Reiner grouping elements into triplets, which he called triads. Fast forward a bit to 1865, and Newlands tried organizing them almost like a musical scale, noting that every eighth element shared properties. He called that his law of octaves. Then came 1869 with Mendeleev's famous mass-space layout. And finally, in 1913, Moseley refined the whole thing with the modern rule based on atomic number instead of mass.
We literally have to pause here to appreciate the absolute genius of Dmitri Mendeleev. His masterstroke wasn't just arranging the elements by their properties, the real magic was what he didn't put in his table. He intentionally left blank gaps. He boldly stated that elements simply must exist to fill these holes, and he even predicted what their specific properties would be. For instance, he predicted an element he called Eka aluminum. Just a few years later, boom, we discovered gallium, and it matched his predictions almost perfectly. Mind-blowing, right?
Section 3. Anatomy of the elements. Navigating the map.
Now that we actually have the map, we need to learn how to navigate its geography. The modern grid is organized into 7 horizontal rows, which we call periods, and 18 vertical columns, called groups. So here is the absolutely crucial point. An element's exact position is completely dictated by its electronic configuration. Elements situated in the exact same vertical column have similar outer electron setups. This means they share very similar chemical personalities.
You can actually think of the table as being divided into 4 distinct neighborhoods or blocks. Over on the far left, you've got the highly reactive metals of the S block. Over on the right, the P block is a super diverse neighborhood containing everything from metals to those incredibly stable noble gases. Right in the middle, the D block houses your transition elements. They're famous for their catalytic properties. And finally, parked way at the bottom is the F block, the inner transition elements, many of which happen to be radioactive. Within those neighborhoods, there's a pretty sharp geographic divide. The left side is completely dominated by metals. They're your good conductors, they're malleable, they're ductile. The right side is home to the nonmetals, which are brittle and generally pretty poor conductors. And acting as the sort of border patrol right between them are the metalloids, like silicon, which have this fascinating mix of intermediate properties.
Section 4. Decoding periodic trends. Your chemical superpowers.
All right, this is where you finally gain the ability to read the table's hidden patterns. First up is ionization enthalpy. I want to slow down just a second to make sure we really grasp this piece of jargon. Simply put, this is the amount of energy it takes to forcefully rip an electron away from an atom. Highly reactive alkali metals, they easily give up electrons, so their energy requirement is really low. Noble gases, on the other hand, stubbornly hold on to theirs, so their required energy is incredibly high. Next, we have the exact opposite concept, electron gain enthalpy. This is the energy change that happens when an electron is added to an atom. Some elements, like the halogens over in group 17, are absolutely desperate for just one more electron to achieve stability. Because of that, they possess the highest negative values for this specific metric.
The third superpower term is electronegativity, which is an atom's ability to attract shared electrons towards itself in a chemical bond. Now, what's really interesting here is that fluorine, sitting near the very top right of the map, is the absolute undisputed champion of electronegativity. It aggressively pulls electrons toward itself. No other element even comes close.
Let's pull all of this together into what is basically the ultimate payoff matrix. By looking at directional cues, we can see exactly how moving around the map flips these properties. Notice how moving across a period from left to right causes atomic radius to decrease, while ionization energy and electronegativity increase. But if you move down a vertical group, the exact opposite happens.
Let's reiterate the logic behind just one of those trends to show you how much sense this makes. Let's take the atomic radius. As you move left to right across a period, you are adding protons to the nucleus, which increases the nuclear charge. This stronger positive charge pulls the electron cloud tightly inward, literally shrinking the atom. But as you move down a vertical group, you are adding entirely new, full electron shells. This physically pushes the boundaries outward, making the atom grow much larger.
Section 5. The power of prediction. Predicting the future.
Let's see how to apply your newfound superpowers to actually understand real-world chemical behavior. Take reactivity, for example. There's this fascinating split behavior going on. For metals on the left side, chemical reactivity increases as you travel vertically down the group. But for nonmetals on the right side, reactivity decreases as you travel down their respective columns. They react in completely opposite ways based solely on their geographic placement.
And honestly, horizontal position brilliantly dictates behavior too. Just look at the oxide nature predictor. By simply looking at an element's left to right position, you can perfectly predict if its oxide will act as an acid or a base. Elements on the far left, like sodium, form basic oxides like Na2O. Elements on the far right, like chlorine, form highly acidic oxides like Cl2O7. And the elements right in the middle, they sit on the fence. We call them amphoteric, meaning they can actually act as both.
We also use all this to spot special chemical quirks. For instance, you have isoelectronic species. These are different elements or ions that end up sharing the exact same number of electrons, which leads to related behaviors. It also helps us expect the unexpected, like the totally anomalous behavior of the very first element in any group. Because these first elements are so tiny and have such intense electronegativity compared to the rest of their column, they often act completely uniquely.
So, whenever you see the periodic table from now on, I want you to remember this final takeaway. The periodic table is not just a chart. It's a powerful, predictive tool. You now hold the ultimate cheat sheet for mastering chemistry. By understanding these grids, these blocks, and these trends, you don't have to memorize a million random facts anymore. You can literally predict how the universe interacts.
But the map is never really quite finished. We currently sit at 118 elements, but the universe is vast. Based on all the incredible patterns we've decoded today, what undiscovered elements are still out there in the cosmos, just waiting to fit perfectly into the next blank space on the grid? Something to think about. Until next time, stay curious and keep learning.